Hello, I'd like to thank the organizers of the symposium for the opportunity to record this talk. In this talk, I will present our results on the existence of the value of a Dynkin game with asymmetric information. My name is Nikita, and this is joint work with my supervisors, Tiziana and Jan from University of Leeds. I'll start by describing a classical Dynkin game and the main concepts we study. Then I'm going to introduce asymmetry of information in this setup. Afterwards, I present our main results concerning the games with asymmetric information. And there is also an additional set of slides that I'm not going to record, but have them ready to help me with your questions. They contain some details of our proofs. So a Dynkin game, also known as the game of optimal stopping. I will introduce a game of two players set on finite time horizon and with full information on the structure of the game available to the players. Assume there is a probability space with some filtration and a time interval 0 capital T, and the two players choose stopping times tau and sigma from the time interval 0 capital T. And the game stops when the first of these stopping times occur. Then tau player, the one who chose tau, pays to the sigma player the following random quantity, p. Note that this payoff depends on who stops the game first and on whether the stopping happens before the terminal time capital T. Indeed, you can see that, for example, if tau is smaller or equal than sigma and is smaller than capital T, then the payoff is determined by the process F, while if sigma is smaller than tau, the payoff is determined by another process G. Since tau player is the one who pays this amount to the sigma player, she's called minimizer, while the sigma player is called maximizer. And the quantities they minimize maximizes the expectation of the payoff P, which we denote as N. Now, in this classical setup, one can define the following important concepts: upper and lower value of the game. Note that tau player is the minimizer, so the infimum is taken over the set of all possible taus, and the supremum is taken over set of all possible sigma, because the sigma player is a maximizer. Now, the lower value is always smaller or equal than the upper value. And it follows simply from the properties of the infimum and supremum. But if the equality holds, the game is said to have a value, and the concept of the value will be central in this talk, in particular the question whether it exists or not. This was the classical game, and now we move to the game with asymmetric information that we study. The payoff of this game is identical to the classical game, but we also introduced two subfiltration of the general filtration F that represent the flow of information available to each of the players. Unlike the classical setup where the strategies of the players were Ft stopping times, in this game tau will be an F1T randomized stopping time and sigma will be an F2 randomized stopping time. I will give the definition of a randomized stopping time in a minute. Our goal is to prove, and we prove it, this is our main result, that the value of this asymmetric information game exists. In the literature on games with asymmetric information, different methods based on variational inequalities and theory of viscosity solutions of PDEs are used to prove the existence of the value and to characterize it. These methods require quite strong assumptions on the structure of the game. In particular, the payoff processes F and G are often assumed to be Markov. Our methodology is more of a functional analytical kind, and which allows for the greater generality. I will give more details soon. Of course, our proofs only work under certain assumptions that are listed on the slide. I will not go too much into detail, but here we have an integrability condition A1, which is very common in the related literature, a regularity/continuity condition A2 on the payoff processes F and G, the order conditions A3 and A4 that are again common in the literature, and a very mild and technical assumption on the filtration F. What I emphasize is that one Except for A2, these assumptions cannot be further relaxed, and we have counterexamples showing that. A2 actually can be relaxed a little bit. We relax it in the paper, but I will not have time to explain it here. It's somewhat minor. Again, we have a counterexample showing that it can be relaxed even further. Another thing I wanted to emphasize is that we do not have to impose any restrictions on the structure of the information available to players. Thanks to how general our functional analytic tools are, we don't have any Markov properties, any underlying diffusions, nothing of this sort. And as I mentioned earlier, well, our goal is to prove that under these assumptions, the value of the game exists. But before we can do that, and before we can even define the value in this setup, I need to give the definition of a randomized stopping time. Assume that there is some subfiltration of our general filtration F, and assume that there is a process that we call generating process that satisfies the following properties. It is Kadlak, non-decreasing, adapted to this filtration, and has values between 0 and 1. Assume also that there is a uniform distributed random variable independent of Ft. Then we call the random time when this process first exceeds this uniform random variable a GT randomized stopping time. We know that usual GT stopping times are GT randomized stopping times. And the corresponding generating process would be the process that only has one jump from 0 to 1 at this stopping time. We denote the set of randomized stopping times as tau r. With this definition in mind, we can finally define the value of our asymmetric information game. Recall that P is the payoff the game has, and N is our notation for the expected payoff. Then the value and the lower value of the game are defined as follows. As before, if the two coincide, then the game is said to have a value. The definition is similar to the definition of the value in the classical game, but the infinite supreme are taken over sets of randomized stopping times, and not classical stopping times. And the randomized stopping times are with respect to different filtrations that represent the information flow of the players. It turns out to be convenient to rewrite this game as a game of controls. We prove the following lemma about Ft randomized stopping times, tau and sigma, that the expectation involved in these indicators can be written as expectation of the integrals involving the generating processes of these randomized stopping times. This allows us to express the expected payoff of the game not in terms of the strategies of the players tau and sigma, but in terms of the corresponding generating processes xi and zeta. And with a slight abuse of notation, we denote this functional on the right hand side as n of xi and zeta. The main tool we use after is Sion's min-max theorem. We do not formulate it rigorously here, but essentially it says that a supremum can be swapped with an infimum as long as the spaces over which they are taken and the functionals satisfy certain topological properties. We give credits to authors of this paper for this idea to apply Sion's min-max theorem to prove the existence of the value of a certain full information Dynkin game. Now, our main result, our main theorem says the following, that this equality holds, and therefore the value of our asymmetric information game exists. The theorem can be formulated in two ways, in terms of randomized stopping times tau and sigma, and in terms of controls xi and zeta. On the previous slide, I illustrated why they are equivalent. I will not have time to go into details of the proof, but I will give an example of the game that fits into our framework. Consider a game with the following payoffs involving a scenario random variable I, so sort of a regime or state of nature that will only be known to one of the players. More precisely, we assume that tau player is informed about the outcome of this scenario random variable in the beginning of the game. Her information flow therefore consists of observation of the trajectories of the processes f and g and of the realization of the scenario random variable I. The strategy tau is a randomized stopping time with respect to this filtration f1. And this particular structure of the filtration allows to decompose the strategy in the following way. Essentially, tau I is the strategy that tau player applies if she observes that capital I equals small I. The game fits our general framework described above, and the value of the game exists thanks to our results. We know that the game is very similar to the Markovian game studied in this paper. And that's it. Thank you for your attention. The talk is based on the paper that you can find on the archive. So any questions you have addressed to this paper, or of course, I'm happy to answer them now.